All right, so we're going to do another example similar to the one that we just did in the last example, but there's a difference here. In the previous example, I'll go back to that, we had f prime, and then we had some information about f in the form of what we were calling an initial condition. This time, we have f double prime. So now I have a second derivative that's given to me, and I'm asked to find f, the original function. And I'm given more information. I'm given some information about f prime, specifically that f prime of 0 is negative 30, and I'm given some information about f of 0 is 30. These are both together called initial conditions as well. So what we're going to do is start by finding f prime. Remember, the derivative of f prime is f double prime. So working that in reverse, the antiderivative of f double prime would just be f prime. So f prime of x is equal to the indefinite integral of 19e to the x minus 11x to the fifth plus x squared. Don't forget this dx right here. And we can take this antiderivative pretty directly. So again, 19e to the x, that's going to be its own antiderivative. Here we add 1 to the exponent and then divide by that same number, which is 6. So I get 11 sixths, x to the sixth. Same thing here, add 1 to the exponent, multiply by the reciprocal. So plus 1/3 x cubed, and then we have this plus c here, okay? So this is the most general antiderivative, or the most general version of what f prime of x could look like. The only missing information is what c is. So we can use one of our initial conditions to do that. Now, only one of these initial conditions tells me anything about f prime. So I want to use this one. If f prime of 0 is equal to negative 30, then I can plug 0 into this, set it equal to negative 30, and then use the resulting equation to solve for c. So negative 30 is equal to whatever I would get from plugging 0 into this. Now notice the power functions, x to the sixth and x to the third, are both going to become 0 if I plug a 0 in for x. So I'm not going to write out, negative 11 sixths times 0 to the sixth power. I can see clearly enough these are both going to become 0. Additionally, e to the power of 0 is 1, and multiplying that to 19 would give me 19. So this just turns into 19 plus c. Okay, solving for c, I could subtract 19 from both sides, which tells me that c is equal to negative 49, from which I can go back to f prime of x and replace that c with this negative 49. So now I know that f prime is equal to 19e to the x minus 11 sixths x to the sixth plus 1/3 x cubed minus 49. That's not the answer because we're not asked for f prime, we're asked for f. But this is one step towards getting there. If I want to find f of x, the antiderivative of f prime is f of x. So I would take an indefinite integral of this now, which would look like this. The indefinite integral of 19 e to the x minus 11 sixths x to the sixth plus 1/3 x cubed minus 49 dx. And this is, again, we can integrate this term by term. So 19e to the x is still its own antiderivative. Here, add 1 to the exponent and then multiply by the reciprocal of that. That's like taking this 6 down here and multiplying it by a 7, which is 42. So I get negative 11 over 42, x to the 7th power. Again, add 1 to the exponent, then multiply by the reciprocal. So this becomes 4, and I multiply by 1/4. 1/3 times 1/4 is 1/12. So I get 1/12 x to the 4th. Constants are nice because we just put an x in front of those, but then I get plus a new constant of integration. I'm going to say plus d instead of plus c, only because I've already used c somewhere else, and I don't want to ever imply that these are the same number. They're not. So with this, I can now do kind of a repeat of what I did in the previous step, use this initial condition, plug it into my function, and then use that to solve for d. So if I plug a 0 into my function, it should come out to 30. Plugging a 0 into this is going to cause all three of these middle terms to go to 0, which hopefully is easy to see. This, once again, will just become 19. So the whole thing reduces down to 19 plus d. Okay? It's fairly straightforward. And now at this point, I would subtract 19 from both sides, which tells me that d is equal to 11. So that is going to get plugged back into this d right here. F of x is equal to 19 e to the x minus 11/6. Sorry, I'm using the wrong function. I should be using this one. Not 11/6, but 11/40 seconds. 11 over 42. It's a little bit sloppy, but x to the 7th plus 1/12, x to the 4th minus 49x, and then finally plus that 11 that we just found. So there is my f of x. Okay? All right, one example left to look at, and this is going to be an application problem. So as we have seen all the way back in chapter 2, in the business and economics applications that we look at, derivatives can be used for multiple things, but among those is marginal analysis. So we talked about marginal analysis a little bit back in chapter 2, and we talked about how if you have either a cost or a revenue or a profit function, then the derivatives of those functions are called marginal functions: marginal cost, marginal revenue, marginal profit. And then we talked about how we can use those marginal functions for different things, like approximating the cost of producing the n+1th item, or things like that. But because they are derivatives, we can work those things backwards. So if you're given a marginal function and you're asked to produce the original function that it came from, that would be using an antiderivative. So consider this example. This is going to be the last example that we do in this section. The pastry shop, Beignet and the Jets, had found its daily marginal cost function to be this: C prime of x equals 3 minus 0.06 x dollars per beignet when x beignets are made each day. If it costs the pastry shop $65 each day to make 20 beignets, how much does it cost to make 40 beignets each day? So again, what we're given is a marginal cost function, but the problem is asking for something concerning just the cost of producing things. So we need a cost function in order to answer this question. To get a cost function from a marginal cost function, we would use an antiderivative. So our cost function, c of x, we can find by integrating this, finding the antiderivative. So the indefinite integral of 3 minus 0.06x dx. I want to point something out here really quickly that you've probably noticed, but I haven't really called attention to yet. Whenever you're finding the antiderivative of a function that has more than one term in it. So here we have two terms. There's the 3 and then there's the 0.06x. You need to put parentheses around your function. So any integrand that has more than one term should have parentheses around it. It is very, very common at the Calculus 1, and I've even seen it a lot at the Calculus 2 level, for students to move too quickly through a problem and forget to put those parentheses. It may not end up causing you to get wrong answers, but notationally it means something different if you leave those parentheses off. So just for the sake of accuracy, make sure you include those. If you only have one term, like if your function is just e to the x, you don't need parentheses in that case, but it's really if you have more than one term. Okay, back to this problem. So this is a really simple function to find an antiderivative for. That constant will just become 3x. And then here, that's a power function. I think of that as a first power right there. So I add 1 to the exponent, and then I multiply the number out here by the reciprocal of that. So I'm gonna have an x squared. I want to multiply this by 1/2. That gives me negative 0.03 x squared. And then we can't forget about this plus c right here. Okay, so that's my most general antiderivative, but it's not the exact cost function for this case because I need to narrow it down to a specific function if I want to be able to use this cost function for anything. And that entails finding this c here. So like the previous couple of examples, we can solve for this constant of integration using those initial conditions. In this problem, we have to search through the description to find that initial condition. So right here, it says, if it costs the pastry shop $65 each day to make 20 beignets, how much, blah, 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 blah. This part of that sentence is my initial condition. It's telling me the cost of something, which is what this function does. Specifically, if I want to make 20 beignets, that's C of 20. It tells me that it should be $65. That's equal to 65. There's my initial condition. And that's what I want to use to solve for C right here. So if we set this thing equal to 65, after plugging 20 in, so that's 3 times 20 minus 0.03 times 20 squared plus c. Do the arithmetic here. It's fairly straightforward. You can use a calculator if you need to, but this is actually you can do without too much trouble just using some mental math techniques. It comes out to 48 plus c. Subtract the 48 from both sides, so that c is equal to 17. Okay? Now, I'm going to take that 17, and I'm going to use it to take the place of the c here in my original cost function. So now we have a cost function. C of x is equal to 3x minus 0.03 x squared plus 17. Okay? Finally, did I answer the question? Almost, not quite, because the question doesn't say find a cost function. It says how much does it cost the shop to make 40 beignets each day? So I can use my cost function to answer that question, but that still means there's one step left. All I have to do is plug 40 into this. What is C of 40? 3 times 40 minus 0.03 times 40 squared plus 17. Use either, you can do this by hand, you can do it in a calculator. This one's not that hard to do, but regardless of how you do it, you're going to get 89. Now, this is an applications problem. You should include some units. So it's $89 each day. And specifically, $89 to produce 40 beignets each day. You don't need to write that part, but this should include units, and this is what those would look like. Okay, that's going to be it for 4.1.